Right, okay, it's 20 past. We will kick off. But I think before we do, let's all raise a glass to 20 years of Sigma and to the next 20 years and more. Good health of Sigma.
Yeah, good health indeed.
Right, oh, that's a nice one.
Cheers.
Cheers. Our speaker for tonight, it gives me great pleasure to welcome back Howie Firth. It's not for the first time this year. He was here in January, I think it was. And so I must thank him for taking time out to put his presentation together and do this for us once again. Now, many of you will know Howie, but for those who don't, I'll give you a little bit of his background. Howie has directed the Orkney International Science Festival, one of the longest running anywhere outside of Edinburgh, since its foundation in 1991. A mathematical physicist by training, he has experiences in teaching, broadcasting, writing, and community development. Spare time, where he gets the spare time from, Howie, I don't know. His spare time interests include playing traditional music. So perhaps one day we get you back on and do a bit of that for us. Huh? After graduating from Edinburgh University, where his teachers included Nicholas Kramer and Peter Higgs of Higgs boson fame, he carried out postgraduate research at Durham University. Interested in community development took him into broadcasting and a pioneering new type of community radio station, BBC Radio Orkney. Awards, Howie has many, including an honorary degree from the Open University, an award from the Institute of Physics, and an MBE for services to popular science in the UK. And tonight, he will be taking us on the road to the stars and a path to the planets. So Howie, it is over to you, and thank you once again.
Well, thank you very much indeed, Pete and Sigma and all of you for this very kind invitation. And what an honour it is to be here on not only the 20th anniversary of Sigma, but also, Pete, your own birthday. So it's a real pleasure to be here. And indeed, I'm going to start by going back into the past, right back 70 years to the year 1950, in the middle of the Cold War. And it was a time when science fiction writers looked out into space as a source of hope for the future. There's a, if I just find the right button to press here to change the image. I'm screen sharing.
Try to click on the...
Oh, I've done it. I've done it now. Well, they looked with hope for the future, and the future's here now, and technology's doing some amazing things. And I'm going to start with a story from that time in 1950. It was written by the poet John Berryman, and it tells of an alien spaceship landing in Kansas. The commander keeps saying just one word, Birom, 5 letters, B-E-R-O-M. That's actually the name of the story. A linguist is called in to try to work out how to respond. Meanwhile, the Russians fear that if communications established, the Americans could get advanced technology from the aliens, Russian troops arrive, and there is a standoff and talk of war. And then, suddenly, the linguist, Professor Yancey, who knows the urgency of warning the aliens of the danger, realizes how to decode the language. He pushes his way towards the line of soldiers guarding the spaceship and loudly says, Birom, and 3 more words. He was not to be disappointed. The tractor beam seized him with a steely embrace that he recognized for deepest friendship. He heard the lock clang shut behind him. An enormous surge of acceleration threw him motionless to the floor of the lock. When the crushing weight eased, he knew they were far beyond the stratosphere. Well, that was back in 1951, a year of Korean War battles and nuclear bomb tests. But then, just 18 years later, came an amazing journey into space with the Apollo 11 landing on the moon. And that was the culmination of almost 12 years rivalry between the Americans and the Russians. It started with Sputnik 1 going into Earth orbit in October 1957. Then in April 1961, the Soviet cosmonaut Yuri Gagarin became the first person in space and the first to orbit the Earth. He was followed in May by the American Alan Shepard. That same month of 1961, President John F. Kennedy set the challenge to reach the moon. That would require both the US and the Soviet Union to develop a new generation of rockets. And then in July 1969 came that walk on the moon by Neil Armstrong. Well, that looked to be the moment that humans would set off on a new adventure to the planets of the solar system and even the stars beyond. But there were only 5 more Apollo missions landing astronauts on the moon. The last of these was in December 1972. In all, just 12 people have walked on the moon. Meanwhile, unmanned landings to Mars were progressing, and in 1971, the Russian Mars 3 mission made the first soft landing. In 1976, 2 American Viking probes landed and sent the first color pictures. They showed features like seasonal dust storms and the polar ice caps. In 1997 came the American Mars Pathfinder, landing the first Mars rover called Sojourner. It travelled a few meters around the landing site and sampled rocks. Well, of course, as we've seen, more rovers have followed, and the amount and the quality of those pictures from the surface of Mars makes it seem tantalizingly close. As close as sometimes the pictures we see on holiday snaps, and also sometimes as close as it appears when we read science fiction stories. Now, one science fiction writer particularly interested in Mars was the American Lee Brackett. And in fact, all of us have probably had contact with her work because she was a film script writer, and she was one of the script writers for the film Rio Bravo with John Wayne. She also wrote an early draft for The Empire Strikes Back. Here is Lee Brackett writing in 1953 to set a scene on Mars in a wonderful adventure called The Sword of Rhiannon. There it is, the hero Karsh left the canal, turning his back on the Dead Sea bottom and facing what had once been inland. The ground rose sharply to the upper cliffs, much gnawed and worn by time and the eternal wind. And there they are, the cliffs, much gnawed by time and the eternal wind. And really, it just seems the kind of landscape that we could see in parts of Earth sometimes, and we could reach out and touch. Well, the little Mars rovers are out there doing just that. These, of course, are NASA pictures from the rovers. It's tantalizing. You could really pick up some of those rocks. And that just feels like the dramatic setting for a science fiction story, or indeed a normal story of humans. Well, in that same year of 1953, the visionary science fiction writer Arthur C. Clarke wrote a novel called Prelude to Space about the first crewed journey to the moon. The story rounds off with a powerful image. It's the rocket launch. There's a great roar of engines, the dust cloud around the ship, the blazing fire of engines radiating out of the heart of the cloud. Up it rises into the sky, and eventually the bright white flare fades away. Written in 1953, he predicted that the actual first takeoff of the expedition to walk on the moon would be 1978, which was, of course, 9 years later than what actually happened with Apollo 11. But in this book, there is an epilogue. It's set a little more than 20 years after the first journey to the moon. It's set at the turn of the 20th century. The young man who watched that first rocket is now standing in a moon base, a city of 5,000 people living under a great dome. He runs his fingers over a piece of sandstone brought back from Mars and looks ahead to his opportunity to travel there, because ships are soon to go into service from the moon. And Mars, he knows, will be the springboard for the leap to the outer planets. And this is the clue about the moon. This is the clue, in fact, why this talk marking the 20th anniversary of Sigma is not being given from a moon base with a Sigma member being one of the staff of 5,000 there. That's what Arthur C. Clarke expected. And the reason why it didn't happen, as he predicted, is that he realized that the only way to build up the long-term exploration of space is to do it in stages. In this book, Prelude to Space, the rocket taking off from the Earth has two parts. Alpha is the ship that actually travels to the moon, but it travels from Earth orbit. Beta lifts her there, parks her in orbit for a time, fills her with fuel, and then Alpha takes off. So Beta is a true shuttle going back and forth between the ground and Earth orbit. Alpha's role is simply the journey from orbit to the moon and back. Now, of course, this is so different from what actually happened when we reached the moon in 1969 and what's happened since. We're all familiar with the massive three-stage rockets, the first two stages of which burn up their fuel and fall into the sea. Arthur C. Clarke's approach was to build up traffic at key hubs. First comes the shuttle, going back and forth into Earth orbit, a bit like us, taking our cars to Inverness Airport and parking there. Then, in the orbit, a big space station for docking, and spacecraft travel to the moon and onwards. And notice how much easier it is to go to Mars if you start from the moon, which is only 1/6 of the Earth's gravity. Now, Arthur C. Clarke's track record at predictions for space is pretty good. This is, after all, the man who predicted geostationary communications satellites. Back in 1959, he was describing how one day these satellites would be used for global TV through hundreds of channels to anywhere in the world. This is the man who predicted mobile phones and said that we'd each have a personal transceiver so small and compact that everyone has one. He said the phones would have means for global positioning, and even that the time would come when we would be able to call a person anywhere on Earth merely by dialing a number. Now, he made those predictions in the days when a telephone was rather a big, black, heavy object. Then you dialed with a kind of finger on a rotating dial, and even to speak to someone in the next parish, you actually had to dial O for the operator so that they'd connect you. So Arthur C. Clarke really was pretty far-seeing in his predictions. And of course, with mobile phones and satellite and communication satellites, we followed his advice, but we didn't do so for space. We didn't put in the necessary infrastructure. Instead of building networks of local airports and car parks, we've been trying to take pot shots at the moon. And that's the context for the significance of what Elon Musk did last week. He wants to make the journey up into orbit simpler and cheaper, so that it can then facilitate all the other stages that can follow. He's reduced the three-stage system to two by building a more powerful rocket, the Falcon. Instead of burning up all its fuel and dropping it into the sea and losing it, the Falcon uses its engines to get back down for a safe landing, and then it can be reused. While it lands, the Dragon space capsule goes on to the International Space Station. And the Dragon and Falcon developments have revitalized space exploration and taken forward Elon Musk's dream of landing on Mars. Interest is also growing in ideas developed over the years for a true shuttle that can fly direct to orbit. And a true shuttle is needed because NASA's space shuttle was only partly reusable. It did take off with its own engines, but it also had two big rocket boosters attached. When the boosters' fuel burned up, they were released, they were parachuted down into the sea, they were fished out and rebuilt and reused. So it was reusable, but in a roundabout way. The shuttle did have wings to help it glide back through the atmosphere. So it was neater than a three-stage rocket system, but still complicated compared to the simplicity with which we fly a plane today from one part of the world to another. The underlying problem is that to travel into orbit involves two different types of situation. in the lower atmosphere, you can fly with a jet engine because, of course, there's plenty of oxygen in the air for a jet to use to burn its fuel. But as we move up through the atmosphere towards space, the air becomes too thin to provide enough oxygen. That's when a rocket engine comes in, solving the problem by bringing in the oxygen in liquid form or as part of some appropriate fuel. So we need two types of engine, one to burn oxygen gas in the lower atmosphere, the other to burn oxygen in liquid fuel as we go up into space. An engine is now in the process of development that will combine the two into one. And this is the Sabre engine that's been developed by Alan Bond's team at the company called Reaction Engines in Oxfordshire. And it is totally brilliant. It combines the two in a single engine, which out towards space uses its liquid oxygen fuel tanks. And then in the lower atmosphere, it breathes in oxygen from the air and liquefies it in an incredibly short time. It breathes the air in, and so quickly, there's a diagram of it, you could see the air, there's an air intake there. It breathes it in and it cools it at an incredible rate so that it can actually enter the engine as a liquid. It's a most extraordinary engine, and it will drive a rocket plane called Skylon, which can fly direct to Earth orbit and take up to 11 tons of cargo at a time to the International Space Station. So this is going to be a revolutionary development. Almost certainly the most revolutionary development in aviation since the jet engine, because it can also fly on the Earth and it can link cities on different continents. It looks like being the dream, the Arthur C. Clarke dream of the big step one on the path to the planets. Step two would be to build a docking station, a proper full-scale docking station where the shuttles can land, but where also rocket-powered spacecraft can set off to the moon. Step three then would be to build the moon base so that the moon can not simply be explored, but can also be used as a docking station for the next stage of the outward journey, this time to Mars. But that's the moon, that's Mars. What about the other planets? Well, there are problems with a number of them. For instance, if we want to go to Venus, it's got a surface temperature of 450 degrees centigrade, a temperature at which solder would melt. For an answer to the challenge of Venus, we can turn now to the man who could well be said to be the heir of Arthur C. Clarke. That, by the way, is Skylon. It's a most beautiful, beautiful design that's powered by the Sabre engine. So that's Skylon. And now here's the man, the heir to Arthur C. Clarke, Geoffrey A. Landis, next to an array of devices and a scene which looks like very much like the Martian surface of which he dreams about. He's a long-time member of NASA's Mars teams. He's been very active on developments with Mars rovers and also photovoltaic systems to capture solar energy to power them. He's a leading member of NASA's Institute for Advanced Concepts. He works on long-term strategy for space exploration. And he's also an award-winning science fiction writer. He's a true visionary, and he's developed a strategy for the role of robots in space exploration. For instance, he says, you could have a robot. Now, this is an actual one that's being tested out. You could have a robot like a mule to follow you around. It would hold tools. It would store rock samples. It would be a bit like a golfer's caddy cart. Here's an artist's interpretation of what it might actually look like on the surface of Mars. And there are the humans out there, and there is the vehicle, the robot vehicle that can follow them around. He says you could also have a solar-powered Scout aeroplane that you could launch by hand. So you could send that round about you to find out the best direction to travel. But he says we could go much further. We could actually have the robots doing it on their own. We could, for instance, stay in orbit around the planet, whether Mars or whether the very hot Venus, stay in orbit around the planet with telerobots on the surface doing the actual exploration. Now, this would save enormously on costs, because if humans are to land on Mars, you've got to get complex systems to keep the humans alive with air and food and many other things. And if you're taking machines down, you don't need all that expenditure. And not only that, if you're not actually physically flying a craft down to the surface of Mars, you don't need then so many skilled pilots. You can afford to give some of the space to take a geologist or a biologist to go on the mission and control then the exploratory robot from orbit. The huge advantage of controlling from Mars orbit as compared to controlling it from Earth, as now happens with the Mars rover, is the sheer amount of time it takes for radio control signals to go back and forth. It's actually close to 2.5 minutes for light or radio waves to get from Earth to Mars. So any control on the Mars rover from here, there's a delay of that amount of time for it to be implemented. And similarly with feedback in the other direction. And this is what Jeffrey Landis says about the advantage of robots doing the work. Tele-exploration from Mars orbit, he says, allows human virtual presence at a wide variety of locations. So doing it from orbit with an orbital base controlling surface and telerobotics, the human explorers are not stuck with one base location. They can explore all over Mars. They can explore the polar caps, near equatorial canyon regions. This frees the mission from landing site constraints. There's no longer a need to select a site like grabbing out of a bag. You can go to them all. Paleolake sites, riverbeds, volcanic calderas, lava tube sites, layered terrain, canyons, possible shoreline features, the North and South poles. Mars, says Jeffrey Landis, is a huge planet. So why camp in just one place? Well, that's Mars, but Venus also could be solved by robots. He points out that on Venus, it's the surface that's very hot rather than the atmosphere. The thick clouds on Venus are creating a greenhouse effect, capturing so much solar heat that the surface heats up, but the atmosphere itself is a similar temperature to our own on Earth. And the atmosphere of Venus is carbon dioxide, heavier than our own atmosphere. So that means it would be possible for some kind of container with our own breathable atmosphere aboard to float. You could imagine some kind of balloon, some kind of airship even. So he says we could float in the atmosphere and send the robots down to explore the surface of Venus remotely. He goes on to say that telerobotic exploration opens up the whole of the solar system. So for instance, with some of Jupiter's moons, with interesting potential for life, they also have intense radiation, which makes it difficult for humans, but that wouldn't stop robots. But that's a vision of how far we could go, but it's going to take time. And the reason it's going to take time is just look at these distances. If we start with the Earth to the Moon, call that one unit, 239,000 miles, and it takes 3 days. And it's quite difficult to do because not many rockets have landed there since the last manned one in 1972. But if we want to go further to Mars, look at the difference. At its closest, it's 339 million miles. So you're thinking of looking at a journey of 7 months. And to go to the vicinity of Jupiter, it's building up now, 365 million miles. That's something like 6 years. And of course, Jupiter is by no means the furthest part of the solar system. And if we want now to think of going further, to imagine that we could spread and explore the various planets and moons of the solar system, whether directly or through telerobots. If we want to go further and wonder about traveling to the nearest star, Alpha Centauri, now there's a challenge. The distance is about 4.37 light years. And with the speed of light at around 186,000 miles a second, It takes a second for light to get to the moon, but it takes it 4.37 years to get to Alpha Centauri. This is how Geoffrey Landis describes it. It's a rather colourful way. If Ice Age humans had launched a starship to Alpha Centauri at the speed of Voyager, the Voyager spacecraft, at the end of the last Ice Age, 11,000 years ago, it would be less than 1/6 of the way through its journey. Now, this is extremely frustrating to get all these wonderful pictures of the cosmos from the expeditions like Voyager, from the Hubble telescope, all these wonderful pictures from distant parts of the universe. But to think that even to get through the solar system is going to take us 50, goodness knows how many years, but to get to
Lost your sound, Howie.
Yeah.
Oh.
Am I back?
Yes.
Oh, good. I'll just say that again then. To get to Alpha Centauri, we need to brainstorm. Is there a faster way than our existing rockets? Well, we could try to build a bigger rocket with more fuel, but there's a snag. If you have more fuel on the rocket will be more massive. And if it's more massive, it will need even more fuel to keep it at its existing speed, let alone drive it forward. It turns out that in order to make a rocket go twice as fast, you have to put on board 4 times the fuel. To treble the speed, you need 9 times the fuel, and so on. It's an exponential curve, and very soon you find that to get even a respectable speed to Alpha Centauri, you need to have the entire mass of the Earth as the fuel of the rocket. So chemical fueled rockets are out. What about nuclear ones, which Arthur C. Clarke indeed envisaged for the first journey to the moon? Well, atomic fuel will certainly provide much more concentrated energy than chemical fuel will. The design of a nuclear-powered rocket would involve a fission reactor on board generating heat. That heat would produce a jet of hot gas coming out of the rocket exhaust at a tremendous speed. But the speed of a rocket turns out to be governed by the temperature of the gas that's coming out of the exhaust. And heating gas from a nuclear reactor can't actually get the temperature hugely higher than the temperature of a chemical rocket source. So even though you get more energy aboard in the form of the nuclear reactor, you can't still get it out fast enough through the rocket exhaust. Now, this has led some people coming out with an idea for driving the spaceship by actually dropping small nuclear bombs outside it, with the force of the explosion hitting a pusher plate. This is actually quite serious. This is, I must say, I would not like to be on the crew of this particular spaceship, but they have a detonation point down there. The bomb goes off there. Colossal blast hits the spaceship. It hits the push shield. The shock absorbers have to brace themselves, and the crew are hopefully at a far enough distance to survive. And there are other ideas as well. And in fact, that idea did lead to members of the British Interplanetary Society coming up with the idea of an interstellar starship powered by nuclear fusion. And this was what it looks like. It was called Project Daedalus. A group of them worked on it quite a few years ago, 1973 to 1978. It looks like this. They proposed manufacturing 1 gram pellets of a frozen mixture of deuterium and helium-3. The 2 gases would be mixed, frozen into these pellets, and then high-energy electron beams would compress the pellets and trigger a micro-explosion from each. And the British Interplanetary Society team calculated that if they could get this process to work, and they had sufficient fuel on board, it would be possible to get to up to 12% of the speed of light, just about 1/8 of the speed of light. Now, they were looking at traveling to Barnard's star, which is 5.9 light years away. And at that speed, they reckoned the space probe would get there in 50 years. There are snags. One snag is it would take an awful lot of fuel. For a 450-ton rocket, they would need approximately 30,000 tons of helium-3 and 20,000 tons of deuterium. It's difficult to get that from the surface of the Earth, so they proposed mining it from Jupiter. Now, this sounds extremely far-fetched, but Geoffrey Landis's job is to look far into the future and see what's theoretically possible, even if today it isn't. And that's how he sums the Project Daedalus project from the British Interplanetary Society. He says, it's true, it relies on a fusion reaction that has never been demonstrated. True, it requires a fuel that needs to be mined on Jupiter, and so it's not realistic for the near term. But interesting, the next sentence, nevertheless, the Daedalus is a landmark in that the Project Daedalus team examined all the features of the interstellar ship design, and the report remains the most complete study of interstellar ship design ever written. Now, there are further ideas. This is one, a light sail, and this sounds absolutely extraordinary as well. It's there's huge expanses of ultra-thin material which could capture the tiny impact of photons of light coming from the sun or coming from a tightly focused laser beam here on Earth. It sounds absolutely extraordinary, and the material would have to be incredibly light, and the photon from the sun would almost spatter onto it. You could imagine like hailstones, only incredibly light. This shows, these various designs shows how imaginative and almost far from any kind of a picture that we could believe possible you have to get to think of the stars. But by doing it, they're opening up possibilities, and they're starting to get people to think. There is even the hope that it would be possible to create amounts of antimatter and then bring together small and equal quantities of matter and antimatter together so that they would annihilate, creating a massive amount of energy. But that again would require whole new levels of technology, since antimatter by its very nature has to be kept away from contact with ordinary matter. So it would have to be contained in some kind of sophisticated magnetic field. But by this time, with all these remarkable ideas like nuclear fusion, like light sails, like antimatter, the timescales are starting to look extraordinarily large. It could take 50, 100 years to build a state project like Project Daedalus. And indeed, with fusion, you can see how long it's taken here with a fusion reactor on the ground. Every 10 years, people look ahead another 10 years or 20 years and say, fusion's on the way, but it hasn't come. And even if a spaceship could be built along any of these lines with all the new technology required, we've got the fact that it would take 50 years to reach Barnard's star if it could get up to these incredible velocities like 12% of the speed of light. Now, even if we manage to reach Barnard's star in these centuries ahead, Barnard's star is just one of the stars in the Milky Way. And the total number of stars in the Milky Way are about 250 billion, plus or minus 150 billion. 250 billion stars. And the Milky Way is just one galaxy. And some calculations suggest the universe may have as many as 2 trillion galaxies. In terms of stars, it's said that there may be as many stars in the universe as there are grains of sand on the Earth. So here we are in orbit around one little grain of sand and wondering about all the others. And of course, the big question, is there life near any of them? Well, 30 years ago, we didn't know if any other star even had planets around it. And in 1992 came the first detection of an exoplanet. The total, as of last week, is 4,268 confirmed exoplanets in 3,154 systems. Some astronomers suggest that more or less every star will have planets around it. Some planets are closer in to their stars, some are further out. but it seems that around 1 in 5 sun-like stars has an Earth-sized planet in the habitable zone, not too close and hot, not too far and cold. Also, we've been finding out that life on Earth is extraordinarily hardy, with various types of bacteria surviving in conditions of extreme heat, extreme cold, extreme pressure, extreme dryness. All kinds of organic molecules have been identified out there in space, forming, for instance, on grains of dust in gaseous clouds in the cold and dark. So really, there's a case for thinking that life is something truly universal, not some freak activity confined to the neighborhood of our little grain of sand, but something that can appear naturally around any of the other grains of sand in that whole universe. Well, this is making it really, really, really frustrating, isn't it? To think that all those possibilities exist, and yet it seems to be close to impossible for us to find a way to travel to even one of these other grains of sand to see if there is life there. So the question now is there any way around it? Well, the big problem is the speed of light, which looks to be built into the very structure of the universe in a fundamental way. With anything else like a car or a train, the speed that we measure depends on how fast it's traveling relative to us. So if somebody throws something off a moving train, throws it in the same direction as the train, the speed of the object and the speed of the train add up. If I'm firing a water pistol and I swing the water pistol in my hand as I fire the water coming out will travel with that bit extra speed because the speed of my arm is added to the speed of the water. But this doesn't happen with light. If I swing a torch in my hand, the light coming out of the torch travels through space at exactly the same speed as if it was static. And it doesn't matter if I fly a jet plane at a colossal speed and point a torch, the speed of the light from the torch is exactly the same. This is telling us that there's something fundamentally different about light. We speak about light as if we are creating it and we happily switch it on and switch it off. Here we are. I very proudly can say, look, I'm switching light on and switching off and feel that I'm some way dominating, that I'm actually making light happen. But the situation really is if light is almost there all the time. It's a bit like a scratch card. When I draw my nail over the scratch card, I don't actually produce a picture. I simply reveal the picture that's there. So it's as if light, we could think of light as something almost like deeper down between the material world that sometimes comes to the surface. And all that is telling us is that light and the speed of light are built into physics in such a fundamental way that a faster than light drive, for instance, as we hear about in a science fiction story, is actually going to be extremely difficult because it seems that there's a brick wall against it. However, there are hints that there is a deeper level in physics, just hints, tantalizing hints. And there is a huge difficulty in bringing together the physics of the very large with the very small. For nearly a century, people have tried to bring together general relativity, the theory of space, time and gravity, the theory of the universe on a cosmic scale, to bring it together with quantum theory, the theory of nuclear and subnuclear particles, the universe on a microcosmic scale. They've tried for nearly a century, and still we don't have a theory of quantum gravity. But there are just a few glimmers that might point to a possible new direction. And now we're moving from the edge of known science into areas that are more like science fiction. But the aim of science is to explore the unknown, and to explore the unknown, you have to begin by probing it. One clue as to something deeper is that if two electrons interact, their spins line up in opposite directions. We say that the electrons, when they interact, become part of a single quantum state. The two opposite spins cancel out to zero. We can actually picture that there. Here's two electrons. They look quite friendly, so they're called Alice and Bob. And there's two electrons. And that lower picture is what normally happens if two electrons interact. One goes spin one way and one goes the spin other way. Now, suppose we bring the two electrons together, like we call them Alice and Bob, and there they are. When they're brought together, it's a fact of the quantum world that they don't actually have a definite spin. It's as if they've got a lot of possibilities, as if life is a bit richer and more complex. And then when we decide to measure the spin of one electron, click, we do it, and we find it'll either be a spin up or a spin down. As soon as we've done that, when we measure the spin of the second electron, we find it's the opposite. Now, the strange thing about this is we can start with two electrons in a quantum state, and we can pull those electrons apart, and we can pull them as far apart as we want. Experiments have been done so far in matters of kilometers or 100 kilometers. But as far as anybody can ever measure, this is instantaneous. When you make the measurement on the first one, it drops out. It drops out of that mixed quantum state. But the second one, wherever it is, as far as we think in the universe, wherever it is going to drop out into the exact opposite. And the thing is about this spin up and spin down, it doesn't matter what direction you choose as your measurement line, the electron will either be the one direction, forward along the line, or backward along the line. Now, this is absolutely extraordinary. It's called entanglement, and it looks to be the fundamental, the essence of quantum theory, because when we measure the spin of the second one, it is always opposite to the first one. Now, this is a bit like if you were outside a darkened room and you hear movement inside the room. You come in, you turn the light on, and you see a figure frozen, absolutely frozen in mid-movement. And then you look around the room and you see a second figure also frozen, facing the first one. You think this is weird. You go out of the room. You go back into the room, switch the light on again and look. Yep, there's the first figure now facing a bit of a different direction. You look, the second figure is exactly opposite. You keep doing this, and every time you find they're in the opposite direction. Well, there's only one conclusion you can come to. Their motions must be coordinated in some deeper way. They must be in a kind of dance, which you disrupt when you open the door and you switch on the light. This then is entanglement. The concept was proposed in a paper written by Einstein in 1935 with two collaborators, Podolsky and Rosen. There they are, Einstein, Podolsky and Rosen. It's called by their initials, EPR. For a long time, it was thought to be hypothetical until the time came when technology was sensitive enough to do this kind of measurement. And now it's at the very heart of the theory. What this is telling us is that deep down, far from there being simple building blocks of matter, like a set of toy bricks, there is something complex and delicate and sophisticated. It's actually suggesting that our whole language of fundamental particles needs rethinking. We're used to building up with our child's wooden blocks. We're used to building up things. We're building up with Lego blocks. But it looks as if when we go deep down, instead of finding things that are fairly inanimate, like Lego blocks, there's something much richer and more complex and delicate and sophisticated. It suggests that there's a deeper level of reality, the quantum state, which is somehow beneath space and time, a level of instantaneous connection. Now, while that's been developing at the level of the very small, a concept's been developing at the level of the very large, again about direct links that seem to cut through space and time. This is the concept of a wormhole, and it's spoken about in terms of immense forces on a cosmic scale. For instance, the kind of forces involved in a black hole. And the idea basically is that in conditions, extreme conditions, somehow a connection can be opened between two parts of the universe separated in space and time that connects them. But again, of course, the forces are such a colossal that this is hardly something that even in the most amazing science fiction could help us to get to the stars. But it's a glimmer, just a glimmer, that is suggesting that far from being at the end of physics with a theory of everything, we might in fact only be at the end of the beginning with the really challenging work still to come. And that then means that although we see these apparent brick walls to these dreams of traveling to the stars, maybe over centuries, one of these glimmers, whether it's entanglement or whether it's wormholes, may lead to something. And here's one more glimmer. Now, this time it comes from quantum field theory. In field theory, instead of thinking of these building blocks like electrons and sticking them together like Lego blocks, in quantum field theory, we have something very abstract. We replace that particle-like electron with an electron field that has different energy levels, and the electron energy levels can rise, and that's what we see as particles, like a kind of condensation in the quantum electron field. And when we go down through the energy levels, something very strange happens, because the lowest energy level that the quantum field can have, the electron quantum field can have, the so-called ground state, is not zero. It seems that what we think of as a particle is something a bit like a mushroom that we see on the surface, but that is growing from a body of fungus underground. There seems to be this deeper energy level, a kind of bedrock. Here's how this strange situation was described by a particularly insightful physicist, David Bohm. That's David Bohm, who was interested in ideas about the human mind and said some deep and profound ideas about that. But this is how he talks about this strange thing about energy. He says, the present state of theoretical physics implies that empty space has all this energy, and matter is a slight increase of the energy. And therefore matter is like a small ripple on this tremendous ocean of energy, having some relative stability and being manifest. Well, this immediately leads to the question, could we somehow access that energy? If it's the case that all space, whether there's matter in it or whether it's a vacuum, that all space has this deeper level, this energy of the quantum field, is there any way that we could access it? Well, so far the answer is no. It's a kind of bedrock, and even how to ask the question is difficult. But it could be that this is a little glimmer that's telling us that the door to traveling to the stars is not completely closed. Suppose the rate of science goes on for 50 years, 100 years, 200 years. There are going to be new developments and new ideas, and this could be one of the directions that opens up the new ideas. And this is actually vital, because it's deeply built into us as humans to wander and explore. If that drive is thwarted, all kinds of pressures build up. And in a way, the biggest challenge in the world today might be seen as not climate change or viruses, or huge as they are, because we do have the technical ability to solve them. But what we lack is something that could be fatal. It's the moral determination to deploy the solutions, to work together to prioritize the need to tackle as an entire world, country, all the countries, all the people, the 7 billion of the people of the world, to tackle the problem and solve them. It's as if we're collectively asleep, and in periods of history where people become collectively asleep, one of two things happen to wake them up: either a catastrophe that could, in our case, could destroy us, or a stimulus or something new. And that's something new, is to feel that we're back on the open road, hitting off on a new journey. Carl Sagan said this so well in his wonderful book, Pale Blue Dot, in 1994. And his are the words to round off this 20th anniversary talk for Sigma: looking ahead with optimism to what might be the subject of the speaker for the 40th anniversary talk and the 60th as well. For all its material advantages, the sedentary life has left us edgy, unfulfilled. Even after 400 generations in villages and cities, we haven't forgotten. The open road still softly calls, like a nearly forgotten song of childhood. We invest far off places with a certain romance. This appeal, I suspect, has been meticulously crafted by natural selection as an essential element in our survival. Long summers, mild winters, rich harvests, plentiful gain, none of them lasts forever. It is beyond our powers to predict the future. Catastrophic events have a way of sneaking up on us, of catching us unaware. Your own life, or your band's, or even your species might be owed to a restless few, drawn by a craving they can hardly articulate or understand, to undiscovered lands and new worlds. Herman Melville in Moby Dick spoke for wanderers in all epochs and meridians. I am tormented with an everlasting itch for things remote. I love to sail forbidden seas. Thank you.
That was brilliant, Harry. Thank you very much. Richard's going to handle the questions. I think we've got 5. Are you there, Rich?
Yes, I am. So yeah, that
Put
was
your video on so we can see you.
okie dokie. Yes, that was a very interesting and fascinating talk as always, Howie. Well done. Great. Now we've got a few questions anyway. One from Martin De Vries here. When do you think Skylon will be a reality?
I should have checked this tonight, because some years ago when I looked, they were talking of 2020 being the first flight. I need to check. I know that I did look at the Sabre engine, and the engine seems to be passing all its tests, but I'm not sure of the time. I would have thought it must be 2022, 2023, that sort of time scale. And I think what's also significant, and why we can be hopeful, is that it's getting steady investment, governmental investment and private sector investment. But I would need to check the date.
Okay, Harry, thanks for that. We've got a question from Eric of Highland here. Developing engines, craft, processes, operations to get into space demands massive intellectual, financial and material resources. In your opinion, is it better for motivated individuals like Musk and or nations to pursue this in some form of space race, or would international cooperation be the way to go?
Yeah, I think it's both. I think Elon Musk has kickstarted. One of the I've heard it said that one of the problems that NASA have had is the sheer size of NASA. They have factories, for instance, in various places, and then it becomes a very powerful influence to keep that factory going, even if the factory is making something that you want to phase out. Say 3-stage rocket systems. There are several thousand people probably in a factory making things like that. So you get a kind of drag against innovative ideas. And actually, it's interesting that rocket planes were flying. The Americans had the Bell X series in the 1960s that were flying at several times the speed of sound. And then they went away from rocket planes, so that the private sector can sometimes innovate when the public sector has more difficulty. But I think we maybe need somebody to do what John F. Kennedy did in 1961, or somebody to speak to the equivalent of John F. Kennedy and tell countries and point out to countries, maybe it's one of two things. Maybe it's that their national prestige depends on them being the first, wherever it is, to produce something, or actually that their economies could benefit very considerably by space technology. And if only we could do, because what Kennedy did was really quite wonderful, that competition between America and Russia to build ever bigger intercontinental ballistic missiles pointed against to each other, he managed to convince both his own people and the Russians to turn that into a competition to look outwards to the moon. So maybe it's a combination of the private sector and the visionaries.
Okay, right, questions from Sven Hunter from Orkney, actually. Howie, great talk and fabulous pictures. If you were suitable for selection, would you want to travel to Mars?
You know, I think so. There's one of these. I remember. I love these science fiction stories, but there's one by an American writer called Theodore Sturgeon, and it's about somebody who you can see has clearly survived a crash and hasn't got long to go. And the last words in the story are, you know, we made it, he says, dying on Mars, which sounds a bit fatalistic, but you know, just imagine going and standing. I mean, it's the ultimate experience, isn't it? You know, if somebody says you've actually got the opportunity to stand on those rocks, to pick up those rocks, to look at that landscape and those cliffs, it's extraordinary. To think that only 12 people ever have stood on the moon, and you think what it must be like to stand on Mars. So yes, I will sign up.
Great, well done, Howie. I'm glad to see that you'd be a candidate anyway. Yeah, another question from Sven here. Matter and antimatter, what's the theory behind directing the energy in one direction rather than just having a big explosion in all directions?
Oh, that's a good one. You see, I think that the whole idea of you know, bringing matter and antimatter together, I just cannot see how anybody's going to do it. Swain's absolutely right. You bring the two together and you just get this almighty explosion. I suppose then somebody goes back to this design of, I think it was the Orion, called the Orion spacecraft, when you fired out fission bombs and the explosion drove you forward. I think I find it very, very difficult to imagine. And I think the reason that people come out with these ideas is, you know, to stimulate more. But I find it very difficult to ever imagine how you could drive anything with this from something like that.
Yeah, okay. A question from Eric again here. I don't begin to suggest I understand dark matter or energy. However, I think there is something like 5 times the amount of dark matter than the stuff we can measure. Is it dispersed throughout the It is dispersed throughout the universe, I think. Could it be utilized in some way to propel a craft to star distant places?
Well, that's an interesting thought, because you've got, you know, this is in a sense why we are, you know, at the end of the beginning, because really the bulk of the universe is made of dark. We now know that the bulk of the universe is made of dark matter and dark energy, but we have no idea what the dark matter and the dark energy is. So in a sense, I suppose you could almost say that physics, since the time of Newton, we've come forward a certain amount, but in the time of Newton, people had a feeling of what everything was made for. And now we've actually got the theory of dark energy and matter, which is that the bulk of the universe, we don't know what it is. So I think that we are on the threshold of huge new unknown areas. And actually, this is one of the challenges. Why I think it's positively dangerous when anybody talks of something like a theory of everything, just imagining there's just 2 or 3 equations to be tidied up, because it can actually lead to a kind of a coziness, what's the word, something a bit suffocating and inward looking. And I think it's really important to highlight the things we don't know. And as the questioner says, out of the things we don't know, who knows what might come.
Yeah, it's this beginning of the end or end of the beginning, isn't it? Thing again, yeah. Okay, a question from Martin again here. What about the Bussard ramjet? Or what about Bussard ramjets?
Oh, now this is something I don't know so much about. Could Martin just fill in?
Yeah, can we
more?
call Martin in to get him to,
What I can do from here for you.
yeah, he's right down at the bottom.
Yes, hello, can you hear me?
Yes, perfect, Martin, thanks.
Yeah, I read a few books about this, and Carl Sagan mentioned this as well in his book Cosmos. It's these Buzzard ramjets. I think it's a guy called Buzzard came up with this, where you have this huge kind of scoop that can scoop up, I think it is hydrogen from interstellar medium, and use that as a propellant. I'm not 100% entirely sure what it is, but then again, that's this idea of not having to bring your own fuel with you, Howie. Good evening, by the way, and thank you. This is a superb talk. Forgot to say that.
Oh, great to hear you, Martin, hear and see you, Martin. Thank you very much. And I'd like to find out. I'll like to find out. I'll look up more about that. But you're absolutely right. That's the key problem. You have to find a way of scooping up fuel on the way, because you simply cannot bring it. You cannot bring it with you.
Okay, and we've got a question from Bill Graham here. Super Talk, Howie. Do you think that it will be possible to use nuclear energy to accelerate a beam of ions to high relativistic speeds, gaining free mass to provide thrust?
That's interesting. That's interesting.
I don't even understand the question.
It's interesting because the thing about the great advantage in nuclear energy is that you're getting so much more out of the fuel. I mean, the chemical energy and chemical fuels is really the upper levels of electrons. With nuclear energy, you're going away down, and you're getting, in a way, a bit like the matter-antimatter conversion. You're actually destroying matter and turning it into energy. That's a really interesting thought. And as I mentioned, it was the idea of a gas. The gas thrust was a problem because of the temperature. You need a higher temperature than can be provided by heat exchange into gas. But then if you fired ions out, you wouldn't be limited. You wouldn't have that limitation. That's most interesting.
Yeah, so there's definitely potential there, you would say. Yeah, that's good. Okay, right, that appears to be at the end of the questions. I'll hand over to Pete. I think you've got some club news for us now, haven't you?
Yeah, well, before I do that, I just want to say thank you very much, Howie. Really, really great talk. I'd say we always give our speakers a little gift. Now, I know you've already got one, but I think we'll give you another one. Okay. But what I think we'll also do is we'll get a bottle to give you something to put into it as well. Okay.
You're very
You can get a set. Now, there is a thing going around segment. If you get a set of 6, you then get the decanter. Okay, so I'm not sure. I think you've probably got 3 or 4 now, so I think you're getting close to it. But when we meet up next, I'll make sure I get hold of this. But if I forget, just remind me. Okay. But there's a brilliant talk. Many questions. That's always a good sign of a good talk.